लास्ट लेक्चर को थोड़ा सा रिकॉल करते हैं और यू रिमेंबर दैट वी स्टडीड simple pendulum last time, and in case of simple pendulum, if you remember that it consists of a bob suspended through some string from a particular point of suspension there, and that is be the mean position. This one is the extreme position of the bob while it starts oscillating there. Let m be its mass, then mg is the weight. Mg sine of theta is a restoring force acting on this bob. L is its length of the string, theta is the angle, very small angle theta, from which it has been displaced there. Then the restoring force that can be written as minus mg sine of theta. Minus mg sine of theta equals to the force applied, total force applied on the bob there, that is given by mx double dot there, mx double dot, right? Okay, as theta, your angle equals to arc upon radius, x upon l, then from here we can write x equals to l theta, or its double time derivative, that will come out to be l theta double dot. Okay, if you substitute for x double dot there, it came out to be ml theta double dot. M cancels with this, and for very small value of theta, for very small angular displacement theta, sine of theta is nearly equal to theta there. Okay, then we can write this particular equation as L theta double dot minus G. Instead of sine of theta, I have simply substituted over theta due to this region. Okay, now theta double dot equals to, take this L to the denominator, G upon L this, or theta double dot, it can be written as double time derivative of theta equals to minus G upon L theta. Take this particular term to the left hand side, it will come out to be d square theta over dd square plus G upon L theta equals to 0. You can compare it with the equation of motion of any harmonic oscillator, d square x by dt square plus omega square x equals to 0, or from here omega square, that will come out to G upon L, or omega equals to square root of G upon L. We also know that omega equals to 2 pi by t, so t, that will be equals to 2 pi by omega here. Substitute for omega, and this will give the time period of your simple pendulum there. On the same lines, today we will discuss compound pendulum here. It is, compound pendulum is nothing but it is a rigid body. A rigid body which can oscillate freely across a vertical plane or about a particular axis which actually passes through it. Any vertical plane about an horizontal axis that passes through it. Okay, right? So this is a particular diagram here. This is a point of suspension. Let G be its center of gravity, and this is O. O is a point of suspension. This solid line that shows your rigid body, O is the point of suspension, right? G is its center of gravity. Let it be somewhere here, and let this rigid body or this compound pendulum be displaced through very small angle theta, such that the new G, let that be represented by G prime here, right? If m is the mass of the rigid body, then its weight, that will be given by m into G there, right? Now we have actually applied force in this direction, right? In this direction, right? Now a restoring force will be developed there. Instead, in Instead, we will say that a restoring torque. In case of your rotational motion, the particular word used here is a torque, a rotational torque, restoring torque that will be produced here, right? Due to which this rigid body that will try to come back to the particular to its original position, right? Okay. So the particular torque here that will be given by torque restoring torque. This torque is your restoring torque that is equal to minus the particular force acting on this particular point here in this direction. Obviously, if this particular angle is theta, then it will be mg sine of theta in this direction, and g sine of theta in this direction. The particular force arm, let that be represented by small l. This length is small l. Then we can write it as mg sine of theta, restoring force mg sine of theta, multiplied by the length arm of force arm there, right? And that is your torque in this particular case. Okay. Now, if alpha represents your angular acceleration in this case, right, then this alpha that will be given by d square theta by dt square. This is your angular displacement, its double time derivative is your alpha. Okay. Also, in case of rotational motion, we know that your torque that is written in terms of your moment of inertia I and the product of moment of inertia I and your angular acceleration alpha there, right? Or it can be written as I d square theta by dt square, right? Substitute for torque from this expression. Let this be equation number 1. Right? So substitute for this. So we can write it as I d square theta by dt square equals to minus mg sine of theta multiplied by L. Okay. When theta is small, that in this particular case, if we take this theta very small, this angular displacement is small in this particular case, right? Then sine of theta again nearly equal to theta. Substitute for this here, it will give us I d square theta by dt square equals to minus mg L theta, or d square theta by dt square equals to minus mg L upon I multiplied by theta there. Or this equation can be rewritten as d square theta by dt square plus mg L upon I theta equals to 0. This is again the form of your equation of motion for a harmonic oscillator there. Now compare this equation with equation for harmonic oscillator. d square theta by dt square plus mg L divided by I theta equals to 0. Comparing this equation with equation of oscillator, that is your t square x by dt square plus omega square x equals to 0, right? While you compare these two, you will find that omega square equals to mgl upon I, or we can write omega equals to mgl upon I, its square root. We also know that this omega is nothing, it is 2 pi by t. So this one is your mgl upon I, or t equals to 2 pi I upon mgl, its square root there. Right. This is the expression for your time period in terms of moment of inertia I. Right. Okay. If we suppose that any particular axis that passes through your this center of gravity there, right, and let Ig be its moment of inertia there, right. Ig represent your moment of inertia of the rigid body about an axis, about a parallel axis through G, then from theorem of parallel axis, we can write this I in terms of this particular moment of inertia, in terms of your moment of inertia about the parallel axis passing through your center of gravity Ig plus m into L square there, right? But this Ig, that can be written in terms of your radius of gyration there, in terms of mass and radius of gyration there. This k is nothing, it is your radius of gyration. Radius of gyration, right? Let's substitute for this. I can write it as I equals to mk square plus ml square there, or m k square plus L square there. Substitute for I equals to this in the expression for time period. Let this be equation number 2, right? Therefore, from equation of time period 2, t can be written as 2 pi, it is I upon square root of I upon mgl. So simply substitute for I here, m k square plus L square divided by mgl, right? M cancels with them, take this L square outside, right? So 2 pi within the bracket, rather instead of taking L square, take this L to the numerator there, numerator there. So can I write it as k square upon L plus L divided by G there. I did it in this way. I have written this particular term in this way so that I can compare this expression for time period with the expression for time period of compound pendulum with the expression for time period in case of your simple pendulum, there, right, comparing this with time period of simple pendulum, that is your t equals to 2 pi the root of, I just write it as its length as capital L divided by G there. It is actually small l, right, but I have written it as capital L, reason being we already have the particular parameter L in the expression for time period in case of your compound pendulum, right? If you compare these two, you will find that this capital L is nothing. Rest of the expression is same, right? Only thing that differs is your L. That will come out to be k square upon L and to small l there, right? This capital L is called your length of an equivalent simple pendulum, right? This is now called as length of an equivalent simple pendulum, right? Okay, now this length L, that is actually L plus k square upon L. It is L plus k square upon L, and this small l is the distance of your center of gravity from point of suspension, right? This one, from point of suspension to your center of gravity G there, right? So that means capital L is bit greater than this, right? It is greater by an amount k square upon L. I just read for this here. Alright. This one figure that represents your rigid body there. This is your center. This is the point of suspension here. Let somewhere here lies your center of gravity G. Its length is your small l, right? Then this capital L, it lies L plus k square upon L. Let this particular length, let it be represented by L prime, right? And this, the particular point here, let this be represented by capital C. So this particular length from here to C, O to C, let that be represented by capital L there, right? And this point C is called your center of oscillation. I'm sorry. C is not the center of oscillation, right? Right, it is center of oscillation. The this is the center of oscillation. This is the center of, this is the point of suspension. This is the center of gravity. This is center of oscillation, the new point, which is capital L distance away from your point of suspension, that is named as center of oscillation. center of oscillation. Now these 2 points, these are interchangeable, right? We will see it, we will see their interchangeability here, right? Interchangeable means they can be interchanged with each other, but how? We will see this. This is your interchangeability of centers of suspension and center of oscillation, right? Center of oscillation C and suspension, center of suspension O. These both are interchangeable. We will see their interchangeability, right? Just redraw the particular diagram once again here. This is your rigid body, this is point of suspension O, this is the center of gravity G, let this be the center of oscillation C, this length is L, this length let it be represented by L prime, the total length is your capital, it is your capital L there. So can I write it as L equals to small l plus L prime, right? But this L equals to, this capital L is your length of equivalent simple pendulum, and its value is k square upon L plus L, k square over L plus small l, it is equal to small l plus L prime. L cancels with this, or we can write k square equals to this L goes to the numerator, so L into L prime there, right? Now we will discuss two cases here. First one, if compound pendulum is suspended from your point of suspension O, right? Then your time period, that is given by t equals to 2 pi, within the 2 pi with the square root, it was your k square plus L square divided by L into J, right? Where is that? This one. T equals to 2 pi k square upon k square plus L square upon GL. I am cancelled with that, right? I have written time period in terms of this, right? Okay, this is the case when the rigid body that was suspended from point O, point of suspension O, right? Substitute for k square equals to L prime here. It is 2 pi L into L prime plus L square divided by L into G. Take L common in the numerator, right? That L cancels with a small l. So can I write it as 2 pi L prime plus L divided by G there, right? Okay, this one is the expression in terms of L prime for time period when your pendulum that was suspended from point O, right? Now we just invert these points, right? By inversion I here mean that I simply invert this. I just change this rigid body in such a way that your center of oscillation that becomes your point of suspension, and your point of suspension that becomes your center of oscillation. You just rotate this particular rigid body and simply suspend this rigid body from center of oscillation, right? So this is second part, that if pendulum is suspended from point C, point of oscillation C, right, then straight draw this one again by taking C here, right, G here and O here, right. This one, this is the point of center of oscillation, center of gravity, and your point of suspension. Earlier it was point of suspension there, right? We have suspended this rigid body from this particular point now, right? So this length is your L prime, this length is your L, right? So the particular time period for this case, that will be given by t equals to 2 pi, right, k square plus, it was L square earlier, right, it was L square earlier, right, but now instead of L we have L prime. L prime is the distance of center of gravity, so L prime square here divided by G into L prime, right. You simply substitute for L prime for L in this expression. That will give me the expression for time period in case of a compound pendulum, where your center of oscillation that acts as point of suspension, right. Now substitute for k square here. Substitute for k square equals to L prime here from this expression again. K square equals to L prime, right, plus L prime square divided by G L prime. Again take L prime as common, right, in the numerator, that cancels with L prime in the denominator. So we will have the expression for time period as L plus L prime divided by G, and you can see that the expression for time period in the both the cases, here when the rigid body that is suspended from point of suspension O, and the time period in case of when it is suspended from point of center of oscillation C, the value of time period is same. Right. So these center of oscillation and your point of suspension, they are interchangeable, right. You can also write it as T prime here, right, or we can see that T that comes out to be T prime. T is your time period, time period when pendulum was suspended from O. This is your when suspended from C, right. So point of suspension and center of oscillation are interchangeable, but they can be interchanged with each other. Right. Next part of this article is maximum and minimum time periods of oscillation. Time periods of oscillation. What will be the maximum and what will be the minimum time period of oscillation? I will start with the expression for time period as 2 pi square root of k square plus l square over g. Take taking square on both sides so that we can remove the square root here, right? So we'll have t square equals to 2 pi square within the brackets k square plus l square upon j. Squaring both sides, right? Now take time derivative on both sides. Time derivative. So take derivative with respect to length l, right? So if you take derivative with respect to length l, so it can be written as 2t dt by dl equals to, this is your 4 pi square, right? This one is your k square upon g. As far as your k square upon g is concerned, k square l square divided by g into l is there. So its differentiation, you take this g outside there, right? So it will be k square upon l. So k square will remain as it is, right? Differentiation of 1 upon l, that will be minus l square. L to the power minus 2 will be there, so it can be taken as l square there, right? Plus l in the numerator and 2 in the l square in the numerator and l in the denominator will be there, so it will be l, the differentiation of l, that will come out to be 1, dl upon d, that is 1 there, right? Okay, now this time period t will be minimum in some constant value, so this dt by dl, that should be 0. Dt by dl, that should be 0, right? That means your this particular term t is not 0, that means this particular term, that should be equal to 0. So 4 pi square upon g minus k square upon l square plus 1, that should be equal to 0. 4 pi square upon g is not 0, so can I write it as k square upon l square with negative sign equals to minus 1, minus cancelled with this, so k square equals to l square, or l equals to plus minus k, there we will take only positive value. So the time period that will be minimum when your distance of center of gravity from point of suspension, that is equal to radius of gyration k. That is equal to radiation of gyration k. This one is the case. This one is the case, right? So the value of time period t, in this case t minimum, that will be given by 2 pi, substitute for k square plus l square is there, substitute for k there, and k into j there, right? So it will come out to be 2k square, k cancelled with k, so it is 2k upon j there, right? This is the case of your minimum time period. Or now time period will be maximum when this L that becomes 0. When L becomes 0, obviously this time period T that will become infinite, as L lies in the denominator. L lies in the denominator in case of in the expression of your time period abbreviated, right? That is written, right? It lies in the denominator there, right? While associated with 0, the time period that will become infinite there, right? Okay, I just simply stop this particular topic, this lecture here today. We will discuss the rest of the topics in the next lecture. Okay, thank you.